What's up guys, this is Massey. Welcome to another video. In this video I want to talk about the integrated rate law. So basically in previous videos we saw that the rate of reaction is the function of reactant concentration. It means that for higher values for in reactant concentration we're gonna have a larger value for reaction rate. And it is also useful to be able to express the reactant concentration as a function of time. What does that mean? It means that imagine we have compound A, and this A is the coefficient. A times A gives product, and the rate of consumption of A is going to be described as negative delta A over delta T. We saw it before. Delta means change. And delta A is going to be changing concentration of A per time. So that's going to be the consumption rate of reactants concentration. That's going to be equal to K times A to the power of N. Again, A is the molar concentration of A to the power of N. And this part is called differential rate law for the reaction. Now, depending on what kind of values we have for n, we're going to have different integral rate equation. If n is 0, we're going to have a 0 order. If n is equal to 1, we're going to have first order rate. And if n is 2, we're going to have second order rate law. So when n equals to 1, first order, n equals to 2, second order, n equals to 0, 0 order. Now we have the differential rate law. We need to derive the integrated rate law. So let's start with the first order laws. For the first order law, if we consider this reaction, 2 times N2O5 gives 4 of NO2 and 1 mole of O2. And the rate of consumption of N2O5 is going to be equal to K times N2O5 to the power of 1. So since it's 1, we don't write it, and we have the first order reaction. Now this one is in terms of differential rate law. We need to integrate it in order to get to the integrated rate law. So since the rate of this reaction depends on the concentration of N2O5 to the first power, which means that N2O5 to the power of 1, it is a first order reaction. So since N is 1, we have first order reaction, and then we can, it's going to be something like that, then we can integrate it. After integration, we're going to end up having this integrated first order law, which is saying that ln of A equals to negative KT plus ln A naught. A naught is the initial concentration of A. And how do we do that? It's negative dA, when you write in differential form, equals to K times A. You bring this A in here and T over there. It's going to be negative dA over A equals to K times dt. Then you integrate it from 0 to time t. That's the initial time. That's time t. Initially we had consideration A equals to A naught, and at the end we have just A. So when you integrate it, this part is going to be ln A from A naught to A. And here we have K times t minus 0. So that's going to make it as ln A minus ln A naught equals to, if you multiply by negative, it's going to be negative KT. And you can keep ln A over here, negative KT here, and you move this one to the other side. That's exactly what you had in here. So this is the first order reaction. If you integrate it, you're going to get to this integrated form. And when you graph it, this one is going to be y This part is going to be the slope, independent variable, and here we have the y-intercept. So y-intercept is going to be ln of initial concentration. Slope is going to be negative k. K is the rate constant, and y is ln a. So if we graph it in logarithmic form, t as time, and on the y-axis, if we have ln of concentration, we're going to end up having a linear relation. Let's see an example. It says the decomposition of N2O5 in the gas phase was studied at constant temperature. So 2 N2O5 gives 4 NO2 plus oxygen. So we are going to have the concentration in terms of mole per liter. These are the concentration of N2O5 with respect to time. It says using this data, verify that the rate law is first order in terms of concentration of N2O5 and calculate the value of the rate constant. So we need to find out the value of K. So first of all, we need to find out if this is the first order or not. What we need to do, the first thing we need to do, we need to convert this one into ln N2O5. So ln 0.1 is going to be negative 2.303. Ln of 0.0707 is going to be negative 2.649. Next one is going to be negative 2.996. This one is going to be negative 3.689. This one is negative 4.382. This one is negative 5.075. And time remains the same in terms of seconds: 0, 50, 100, 200, 300, and 400. So when we graph it, we have time in here, and we have ln N2O5 in here. When you graph it, it's going to be something like that. We're going to have linear function. Then after that, we can find the value of K. We know K is the negative of slope, because as you remember in the previous page, it said when you're dealing with a linear function, negative K is going to be the slope. So K is going to be the negative slope. So we find out the difference, y2 minus y1 divided by x2 minus x1. That's going to give me the slope, which is going to be negative 5.075. Just consider this one and the first one, minus negative 2.303 divided by 400 minus 0. That's going to be negative 2.772 divided by 400. That's going to give me negative 6.93 times 10 to the power of negative 3 second to the power of negative 1, or 1 per second. So that's the slope. K is going to be the negative slope. So that's going to be positive 6.93 times 10 to the power of negative 3, 1 over second. So that's going to be the rate constant. So let's see the next example. It says calculate the concentration of N2O5 at 150 seconds after the start of the reaction. So we learned that if we are dealing with the first order reaction, which we had in this situation, it's going to be ln A equals to negative KT plus ln of A naught, which is the initial concentration. So in this example, it's going to be ln of N2O5 negative KT plus ln N2O5 initial. So we don't have this one. K, we already found it. 6.93 times 10 to the power of negative 3. T is 150 seconds plus ln initial concentration is 0.1. So when you calculate it, you're gonna end up having ln N2O5 at t equals to 150 seconds equals to negative 3.343, and the concentration N2O5 at this time is gonna be e to the power of negative 3.343. That's gonna make it as 0.0353 mole per liter is gonna be the unit for molar concentration. Now let's see how to find out the half-life of a first reaction or first order reaction. What does that mean when we are talking about half-life? The time required for the reaction to reach half its original concentration is called the half-life of a reactant, and it is shown by t half or time half. So if I write the integrated form of the first order reaction, we're gonna say that when we are talking about half-life, the t is gonna be t half, and the final concentration is gonna be half the initial concentration. It means that A equals to half the initial concentration. So when I bring this one here and we arrange it, it's gonna be ln of initial concentration divided by final concentration equals to kT. So when you sub it there, it's going to be A naught divided by A naught divided by 2. These two cancel out, and 2 is going to go to the numerator. It's going to be ln 2 equals to K times half-life time. And then you're going to say half-life time equals to ln 2 divided by K. And ln 2 is 0.693 divided by K. So that's how we find out the half-life time for first order reaction. Okay, let's solve this example. It says how to find out the half-life for a first order reaction. A certain first order reaction has a half-life of 20 minutes. Calculate the rate constant for this reaction and how much time is required for this reaction to be 75% complete. So it says the half-life time is 20 minutes, so t half is 20 minutes. And we need to find out the value of K. So we're going to say K equals to ln 2 divided by T half, which is 0.693 divided by half-life time. That's going to be 20 minutes. That's going to be 3.47 times 10 to the power of negative 2 minutes to the power of negative 1, or 3.47 times 10 to the power of negative 2 1 over minutes. Why 1 over minute? Because half-life time is in terms of minutes. And K is going to be in terms of minute to the power of negative 1. Part B. It says how much time is required for the reaction to be 75% complete. So we're going to say ln A naught over A. We had this before. 75% complete, it means that the final concentration is going to be 25% of the initial one. So it's going to be ln A naught over 0.25 A naught equals to KT. So that's going to make it as ln 1 over 0.25 is going to be ln 4 equals to K times T, and T is going to be ln 4 divided by K. K is the rate constant that we found in part A, 3.47 times 10 to the power of negative 2. T is going to be 40 minutes. It means that after 40 minutes, 75% of A is consumed and only 25% of the initial concentration is remaining. Now let's talk about second order rate law. So we have the same thing. A gives products. Rate equals to negative delta A over delta T equals to k times a to the power of 2. So in this case, n equals to 2. That's why it's called second order rate law. So rate of change of concentration of A equals to k times concentration of A to the power of 2. Now if we integrate it, we're going to end up having 1 over final concentration of A equals to k times T plus 1 over initial concentration of A. So that's going to be the integral form of the second order rate laws. Now let's see how to find out the half-life of the second order. Half-life, again, the time requires to be half of the initial concentration. So final concentration of A equals to initial concentration of A divided by 2. When you sub it there, it's going to be 1 over half of the initial concentration equals to k times T plus 1 over initial concentration. So it's going to be 2 over A naught minus 1 over A naught equals to KT. 2 over A naught minus 1 over A naught is going to be 1 over A naught equals to KT. So it means that T equals to 1 over K times initial concentration of A. That's how we find out the half-life time of second order reaction. Let's see an example. It says, let's find out the rate law. It says butadiene reacts to form its dimer according to this reaction. 2 of C4H6 gives C8H12, and here you can see the data collected for the reaction at the given temperature. In the left hand side you see the concentration of butadiene in terms of mole per liter, and the right hand side you see the time in terms of second. So as you see here, as time goes, the concentration of reducing, because that's the reactant. It says part A is the reaction first order or second order. What is the value of the rate constant for this reaction? And what is the half-life for the reaction under initial condition of this reaction? So what we need to do on the first order reaction, we saw that it's going to be logarithmic. That's going to be y. It means that if we find out ln of the concentration and we plot it with respect to time, if we get the linear relationship, it means that the reaction is first order. Now for the second order, if we plot 1 over concentration, plot it with respect to time, if we get a linear function, we're going to have the second order reaction. As you see here, this one is also a linear function. The y is 1 over a, k is going to be the slope, and the y-intercept is going to be 1 over initial concentration of a. So that's another form of linear function, mx plus b. It is especially for second order reaction. So when you plot 1 over a, plotted with respect to time, if you get the line, it means that you're dealing with a second order reaction. If you do it based on ln function, it's going to be the first order reaction. So now you have the time. If you basically calculate ln C4H6 and also 1 over C4H6 concentration and list them here, it's going to be negative 4.605, negative 5.075, negative 5.348, negative 5.599, negative 5.67, negative 5.915, negative 6.028, and negative 6.175. And on the other hand, you have 1 over C4H6, we have 100, we have 160, 210, 270, 320, 370, 415, 481. So that's going to be 1 over the concentration. Now if you plot it you're gonna figure out if you plot ln of C4H6 with respect to time is gonna be the curve. If you plot 1 over concentration of C4H6, you're gonna end up having a line. So it means that the reaction is a second order reaction. So it asks us to find out if it's first order or second order, which we already found that is second order. It says find out the rate constant, which is the K value, and find out the half-life time for this reaction. So let's find out K first. So we're gonna say that the slope in second order reaction is exactly the same as K. So we're gonna say (481 minus 100 divided by 6200 minus 0. So that's gonna be 481 minus 100, 6200 minus 0. That's going to be 6.14 times 10 to the power of negative 2 liter mole per second. So that's the unit of rate constant for second order reaction, which is totally different from the unit of K in first order reaction. You can easily derive that unit. Now let's see part C. Part C, it says the half-life time is going to be 1 over K times initial concentration. As we developed it earlier, I'm going to show you where we had it. We had it earlier here. Half-life time equals to 1 over K times initial concentration of A. So we have both these numbers. We have K and we have initial concentration. So it's going to be 1 over 6.14 times 10 to the power of negative 12. And initial concentration is 1 times 10 to the power of negative 2. That's going to give me 1.63 times 10 to the power of 3 seconds. So that's the half-life time. Now the last part is going to be zero order rate laws. And in this case, rate equals to K times A to the power of 0. So that's why it's called zero order. It means that the rate is completely independent of the concentration of the reactant. Rate equals to the K value, and K is only changing with temperature. It is not changing with the concentration. So if you integrate it, basically it's going to be like that. dA over dt equals to K. It is going to be negative dA K times dt, which is going to be A equals to negative KT plus A naught. So that's going to be Y mx plus B. The slope is negative K, and the y-intercept is going to be the initial concentration. How to find out the half-life time of zero order? Just put it again, the final concentration as half of the initial concentration, and we derive it. Half-life time is going to be A naught divided by 2 divided by K. That's how we find out the half-life time for zero order rate laws. I hope you enjoyed this video. Please leave me a comment if you have any question. Please don't forget to subscribe this channel. You can have access to many other videos regarding chemical kinetics, chemistry, physics, and math. Thank you for watching and have a great day.